In this video, I'll be going over the properties of logarithms. And first up, we have the product rule. So if we have inside the argument of a logarithm a product, so m times n here, we can separate that into two separate logarithmic terms, where we have the first factor and then the second factor. And as an example, suppose we have log, I meant to write b here, log base b of 8k, and we want to expand that. Well, we notice that we have a product in here, so we can expand that as log base b of 8 plus log base b of k. And similarly, if we have two terms like this that are separated by an addition sign, we can go the other direction as well. Now, the reason that the product rule works is we think about logarithms and the fact that they are closely tied to exponents, and anytime we have a logarithmic expression like this, log base 5 of, let's say, 25, that is equal to 2 because 5 squared is equal to 25. What we want to remember is that this value over here is an exponent. Okay, so logs always equal exponents. So if we go back to the product rule, and what it's saying is each of these log expressions is equal to an exponent. And if we think back to how the exponent rules work, if I have 5x to the 5th times x to the 3rd, what we do is we add the exponents. So we end up with x to the 8th. So it's kind of like when we're multiplying here, what we do is we add the two exponential, or the two exponent values. Next, we have the quotient rule. So if we have a quotient inside the argument, here we have m divided by n. We can rewrite that as log base b of m, which is the numerator, minus log base b of n, which is the denominator. Okay, and as an example, if we want to expand log base 3 of x divided by 3y, well, I would say log base 3 of the numerator minus log base 3 of the denominator. And we've expanded it one step, but we notice that this is still a product, 3y. So we could expand that second log expression. So I'm going to subtract. We need to be careful here because we're subtracting this entire term. Okay, so we want to write it in parentheses. So we're going to say log base 3 of 3 plus log base 3 of y. And we could distribute the negative sign through to ultimately end up with log base 3 of x minus log base 3 of 3 minus log base 3 of y. Okay, and the quotient rule follows from the rules of exponents. If I had x to the 5th divided by x squared, what we're going to do is we're going to subtract the exponents. We end up with 5 minus 2, which is x cubed. Okay, so when we divide, we subtract the exponents. So when we divide here, m divided by n, we're going to subtract. And then the third rule is the power rule. So if we have log base b of m raised to the n power, that n, the exponent, can get rewritten as a coefficient, and we're going to multiply there. So as an example, if we want to expand ln of x cubed over y, okay, well, first what I'm going to do is rewrite this using the quotient rule. So this will be ln of x cubed minus ln of y. And then this 3, I'm going to rewrite that as a coefficient of the first term. So 3 ln of x minus ln of y. And that would be it. Okay. So one thing to note that I didn't mention previously, but anytime we're expanding or condensing logarithmic expressions, it's important that the base stays the same as we are expanding. So in this example, ln, remember, is just log base e. So I've kept log base e in each of the expansions, or each term of the expansion. And then let's consider or think about how this relates to the rule of exponents. If I have x to the third raised to the fifth, well, what I do is I multiply 5 times 3. So we get x is equal to 3 times 5, which is x to the 15th. Okay, so what we're doing is we're multiplying there. So let's look at a few examples of expanding log expressions. First up, we have ln of x to the fourth y over 7. So first, let's take care of the fraction. So I'm going to write this as ln of x to the fourth y, and applying the quotient rule, we can rewrite this as so. And then in this first term, we have a product. So we can write this as ln of x to the fourth plus ln of y minus ln of 7. And then the 4 right here can be rewritten as a coefficient. So 4 ln of x plus ln of y minus ln of 7 gets us to a fully expanded expression. Our next one, we have log base 6 of x plus 1 quantity squared divided by y times z. So again, I'll handle the quotient first. So log base 6 of x plus 1 squared minus log base 6 of yz. Okay, so in the first term, this 2 can come down as a coefficient. So 2 log base 6 of x plus 1 minus, because the second term has a product, I'm going to expand that using the multiplication rule, but the minus sign in front is going to get distributed to each term. So it's like this. So that's an okay way to leave it, or if we distribute the negative symbol, what we end up with is the last term becomes negative. And that's it. So going the other way, instead of expanding, we want to take, or be able to take, a logarithmic expression that has multiple terms. We want to write it with a single term. Okay, so what I'm going to do is I'll just, I have 4 terms. I want to get this down to a single term. And these are all log base 10, common logs. So I'll take these 2 first. So log of 3 times 4 minus log of 5 minus log of 7. And then, let's see, I'll just take these 2 next. So we're going to have log of 3 times 4. I'm going to just multiply that out. Okay, so we end up with 2 terms. And again, this is going to be the quotient rule. So we have 12 fifths divided by 7, which is the same thing as 12 fifths times 1 over 7. So the 7 goes into the numerator, or I'm sorry, into the denominator. So we end up with log of 12 divided by 5 times 7, which is 35. So log of 12 over 35. And if we reduce that fraction, I can divide the top and bottom. I thought 3 was going to go in, but it doesn't. So actually, that's as far as we're going to go here. So we have a single term, can't simplify that fraction. All right, and then this next one, we're going to condense this into a single term. So 4, I'm going to handle that 4 at the very end. So this 3 can go upstairs as an exponent, so ln of x cubed minus ln of x plus 5 minus ln of y. I'll handle these two first. So I get ln of x cubed over x plus 5 minus ln of y. And then again, the y is going to go to the denominator of the first expression, or the first argument. So we get y times x plus 5 in the denominator like this. And then the 4 here is going to become an exponent on the argument. So we end up with ln of x cubed over y, x plus 5, all raised to the 4th power. And that's it. The last thing for us to look at in this video is called the change of base formula. And how the change of base formula works is if we have log of some base m, say it's some value, what we can do is we can rewrite this as log with a new base n of the argument in the numerator divided by log base n of b. So m goes in the numerator, this base here, b, goes in the denominator. Now this is really useful when we have a base for a logarithm that is not either 10 or e, and we want to be able to evaluate this easily on a calculator, because not all calculators are we able to change the base number. So for example, if we have log base 5 of 100, we could rewrite this as log of 100 divided by log of 5. So I've rewritten this both with log base 10. I've rewritten these as common logs. And now that these are written as common logs, we can get a decimal approximation easily from a calculator, because scientific calculators at least have a log button, a common log button. So typing this into the calculator, we end up with about 2.8614. Now, let's think about why this makes sense. This expression, log base 5 of 100, is asking 5 to what power is equal to 100? Well, 5 squared is equal to 25. 5 cubed is equal to 125. So the exponent is going to be between 2 and 3, and that's exactly what we found here. And then lastly, we have log base 10 of 18 using the change of base. This time I'm going to change it to base e, so ln of 18 divided by ln of 10. Okay, so what this is saying is, well, let me back up. The reason we do this is because, again, scientific calculators will have an ln button. So we can do ln of 18 divided by ln of 10, and what we end up with is about 1.2553. And again, this makes sense because I want to know 10 to the what power is equal to 18. 10 to the first is 10. 10 squared is 100. So we want our value to be between 1 and 2. Alright, so that's everything we're going to see in this video. And the whole reason we're doing these properties, or looking at these properties, and why they're important, is so that we can ultimately solve equations that have logarithms and exponential expressions in them. And that's what we'll see in a later video.